All right, this is going to be Unit 7 work on intermolecular forces. This is originally for Dallas Grimes AP Chemistry. So here we go. So the first one objective is the biggest one in this unit. It's all about the different intermolecular forces. And so we need to make sure that we have a working understanding of how to identify something as polar or nonpolar, and then how that relates to its intermolecular forces that are possible, dipole-dipole, or dispersion. So dipole-dipole goes with polar molecules, dispersion goes with nonpolar molecules, and then we have hydrogen bonding. And hydrogen bonding is when we have a specific kind of intermolecular force that we see, say, in water or some other molecules that we'll talk about later. But we have to be able to identify those three different kinds of intermolecular forces, and then also look at polarizability, which is question number 2, and how that relates to intermolecular forces. So, all right, here we go. All right, so we have dipole-dipole interactions examples. All of these are polar molecules. Notice that we have this hydrogen fluoride here. This is the only strong acid, the only acid that's a binary acid with a halogen that is a weak acid. And the reason why it's weak acid is because of hydrogen bonding. And so I want to highlight this one, that it goes through hydrogen bonding and not just dipole-dipole interactions. So maybe I'll just actually get rid of that to make sure that's not confusion. That's going to go in a different one. Then we have dipole-dipole. We have dipole-induced dipole. We have dissolved oxygen, which is going to be our non-polar molecule. That goes with our induced dipole, also called temporary dipole. And the water is going to be a polar molecule, so we have then dipole, that's the polar, induced dipole, nonpolar. Ion dipole, anytime we have an ionic solid dissolving in a polar solvent like we have here, ions of sodium chloride in water, that's going to be ion dipole. Then dispersion, all of these are nonpolar. So there we go. Polarizability. We talk about how squishy the molecule is, or how easily those electrons are able to get pushed to one side of the molecule. Because if we have a molecule that is, kind of electron cloud here, and the electrons kind of get pushed over here more than over here. So imagine this were some kind of a very large molecule, and all of these dashes are the electrons, where the electrons could be. We have more of them over on this side, so that makes this slide more negative. This side makes more positive, so we end up with a nonpolar molecule that has a polar moment. And the larger the molecule, the more easily these electrons are able to get pushed to one side. This happens if you put it next to a polar molecule, or it happens just kind of on its own. And we can have induced dipoles working with other induced dipoles, thinking about liquid nitrogen as the example there. All right. This also talks about the diffusion of the electron cloud. So let me draw a little bit more with this, because I left some space here for that particular problem. With those two different molecules, we have N-pentane, which is going to look like this. Carbon to carbon to carbon to carbon to carbon. 1, 2, 3, 4, 5 carbons. And there's hydrogens coming off of each of these carbons. We have 1, 2, 3, carbon, carbon. So there's N-pentane. Here's isopentane. And so N-pentane has this long chain of carbons. And because of that, that means the electron cloud is going to be very diffuse around this thing, and there it can be manipulated more, where this is going to be a compact electron cloud and not as diffuse. And so if we have a greater diffuse electron cloud, we have higher intermolecular forces because we have a higher polarizability. This one here, so both of these have the same, I did that wrong, didn't I? This should be another carbon there. Both of these are going to have the exact same molecular mass, but the one that has a more diffuse electron cloud is the one that's going to have a higher polarizability. All right. Temporary dipole moment is that induced dipole moment where we have the permanent dipole moment, which is the polar molecule. Always going to be a dipole no matter what, where induced is related to the polarizability and how well those electrons or how easily those electrons can be pushed to one side of the molecule or not. Some evidence that all atoms exert attractive forces would be liquid nitrogen. So liquid nitrogen is a nonpolar molecule, and nonpolar molecules we would expect to have no attractive forces, but if we cool it down enough, those molecules start to attract to each other and form liquid nitrogen. Physical properties we could look at for intermolecular forces, the list that we came up with the very first day. Here's hydrogen bonding. We started talking about that at the beginning and how hydrogen fluoride is going to be a polar molecule that does hydrogen bonding, and this is really frustrating because a lot of students think that since it says bonding that we're referring to that bond right there, which is not a true statement. That's not it. We're looking at, say, water, which looks like this. Because it's polar, has a slightly negative side on the hydrogen and slightly positive on the hydrogen. And we could do the same thing with another water molecule. And so it's this attractive force in between the two different molecules that we call hydrogen bonding. And in order to have hydrogen bonding, we have to see this in the molecule. We have to have that bond, specifically one of those three, in the molecule. Because water has two of them, oxygen to hydrogen, and because of its shape, it turns out to have very strong intermolecular forces relative to its size. Number 17, we look at the boiling points. Bromine is going to be nonpolar. Iodine monochloride is going to be polar. That's the difference. Polar has a higher intermolecular force than nonpolar does in dispersion. All right, number 9, we have the different boiling points of molecules, tetra-type molecules bonded to elements from the 14th column. So we have carbon, silicon, germanium, tin. All of these are in the same column of the periodic table. Goes carbon, silicon, germanium, tin, respectively. That means that carbon is going to have the lowest molecular mass, tin is going to have the highest intermolecular mass. So as we go down the periodic table, the boiling point increases because the molecular mass is increasing, which causes an increase in IMF because there's an increase in polarizability. So there's that. Types of intermolecular force. First, all of these have dispersion forces, but the one that I identified is going to be the one that's the most important. So here's dispersion, dipole-dipole. This is a polar molecule. Draw it out if you need to. So there's the chlorine. That is a polar molecule. Same thing with the phosphorus trifluoride. Sodium chloride is going to be an ionic compound, so that's going to have the highest intermolecular forces possible, which really isn't an intermolecular force because it's an ion compound. And we have dispersion here. All right, now we have some hydrogen bonding. The only one here that can go through hydrogen bonding is going to be this one here. None of the others have the bonds that are required. And you have to identify first if those elements are in it and then if they are bonded correctly. For example, this one here would not have hydrogen bonding. because it looks like this. This bond right here is not on that molecule, so it's not hydrogen bonding. Higher boiling point, higher molecular mass here, so higher boiling point, higher molecular mass. And then this one here is the interesting one. This has a higher molecular mass by far, but this goes through hydrogen bonding. So that's going to have the higher boiling point. Hydrogen bonding is much, much greater than dipole-dipole. Xenon, larger mass. Carbon disulfide, larger mass. Chlorine, larger mass. Lithium fluoride, it has ionic forces. It's an ionic compound versus the dispersion forces. Ammonia is going to be higher than the phosphorus trihydride because of the hydrogen bonding that's there. All right. Liquids are closer together than gases. That's why they are less compressible. Surface tension. So surface tension is the attractive forces between the molecules on the surface. That's the first one. And this is not supposed to be right. This is part of the question. Oops, that's my fault. I bolded that. This should not be in red. This is the definition of surface tension. The molecules attracting to each other at the surface. As we increase intermolecular forces, so does surface tension. As we increase temperature, it means that the molecules are moving faster, which means that there's going to be a lower surface tension. So that's an inverse relationship there. Razor blades can float in water because they do not break the surface tension of the water. So we've looked at adhesion and cohesion in class, and we look at the polarity of things. Since glass is polar, we can look at how that's going to interact with the mercury or the water. Since mercury is going to be nonpolar, it's going to attract to itself more than the glass, which causes that convex shape like this inside the cylinder. Where water is attracted to the glass because it is also polar, glass is polar, it tries to climb up the walls, which means that it provides a shape like this. So that's the meniscus. That's what we always see when we fill water inside of a container. So as we fill a glass up to that point where the glass runs out and overfill it, we end up with these cohesive forces that attract those water molecules together, which means that means the surface tension is greater. The cohesive forces create that surface tension, which allows us to overfill the water above the glass. Likes dissolve likes. Oh, I did it again. I turned some of the question into red as part of the question. Back up there. So, likes dissolve likes tell us whether or not something is going to be soluble. So, polar molecules attract to other polar molecules, and therefore will dissolve things. Non-polar molecules attract to each other for the opposite reasons. There aren't any of these polar sides for non-polar molecules, which allows them to attract. If you put them together, then we have things that are polar that are attracted to other things that are polar, and non-polar that are attracted to other things that are non-polar, so that they don't match with each other, so they aren't going to, they're not going to dissolve each other. Some kind of example where we have likes dissolve likes is going to be an ionic compound in a polar solvent, or we could do, so this is ionic solid, and here we have the polar. So ionic and polar works, polar and polar works. So rubbing alcohol is polar, and so is water. So those two things mix. Miscible is going to be liquids. Soluble is solid and liquid. So if we have so this would be not miscible. Not miscible would be oil and hexane. Oil is polar, hexane is non-polar, And so those are some examples. All right, now we can get into learning objective 2, which goes through the different kinds of crystalline solids. So there's 4 of them. We look at ionic, covalent, molecular, and metallic, and the important parts here are what we see at the different lattice points, and then how that works in terms of making it into its solid shape, its crystalline structure, and then its properties, which is going to be the next question. So ionic solids are ionic crystals are going to have the lattice points being ions. So this is sodium chloride. Here's our sodium ions. Our sodium ions and our chlorine ions. And this whole structure then arranges itself in a sodium chlorine fashion, positive, negative, and so on. So this forms what's called a network solid. Covalent crystals, instead of having the electrons transfer from one thing to another to make a positive and negative, we have atoms where the electrons share at each of these different places. And this occurs mostly throughout the entire structure, only that the electrons aren't delocalized like they are in metallic crystals. And anytime we think about a carbon atom, or excuse me, a carbon element, it's going to have this kind of a covalent crystal. So diamonds are very, very hard because of this network that they provide. We have a carbon bonded to another carbon, and so on and so forth. Where graphite, which is pencil lead, have these layers of carbons. So carbons, and so they're just stacked on top of each other. So when you write with your pencil, these carbon layers just slough off of the pencil and are left behind on the paper. We could also look at another one. This is going to be a carbon nanotube right here. And this nanotube then has the different carbons in it, and then it just also then forms into a tube. This has a lot of interesting material science applications. So a lot of research is being done into nanotube technology. All right, molecular crystals. Instead of having atoms at the lattice points, we have molecules at the lattice points. The electrons are going to be locked within that molecule, so they're not going to be able to transfer from atom to atom. And a really good example to this is going to be water. We can see a water molecule right here, a water molecule right here, a water molecule here. And ladies and gentlemen, since we're dealing with solids, this is going to be ice. So water in its solid form. And then we have the attraction between each of them. And incidentally, this is also what makes ice less dense than water. And so we have that. Metallic crystals, it's somewhat of a misname here, a misnomer that we call them as crystals, because there really isn't a crystalline structure. Like we see a crystalline structure here, crystalline structure here, and here, a very definite shape that goes along with everything, where a metallic crystal is more of just a metal. So in general chemistry, we call this metallic bonding. And here we talk about it being a crystal, because the lattice points of this crystal are going to be the ions. This is going to be a cation. So this, if we look at copper, here's the example. This will be a copper atom, and so on, copper atom, where the electrons can go anywhere in this metal. And this is how metals bond to each other. And this is going to be true for any kind of pure metal. Any element on the periodic table that's classified as a metal will go through this kind of bonding and form into what we call metallic crystals. And these electrons, how they are shared evenly through this structure, is what gives metals their properties, which is what we'll look at when we get to the metals on the next part. All right, so we have ionic and covalent. So if we look at ionic versus covalent, they're very similar in their properties, only covalent is very hard, extremely high melting point, and can conduct electricity in just a little bit. Now, for me, when I try to remember these things, I don't memorize the properties. Instead, what I do is I memorize the example. And then I start thinking about the properties of that example. Sodium chloride is hard, it's brittle, has a high melting point, does not conduct electricity, and that helps me remember all of the different properties of it, where covalent is going to be our diamond. And so diamonds are very hard. It's the hardest natural substance known, has an extremely high melting point, and this is one that you'd have to remember. It does conduct electricity a small amount, and this is important. This has some important applications. Molecular crystals is going to be the water. And you're like, well, water is hard, right? Well, not when we compare it to the other things. Like if we were to take ice and they were to take a diamond ring or diamond something and then scratch it across the surface of the water, or excuse me, of the ice would not give any problem to that whatsoever. The diamond would just scrape it off. Or even if you take metal like iron or like a steel scraper to scrape off your sidewalk, it's going to scrape that ice off pretty easily. So this is soft relative to the other things. It's also somewhat flexible, can be shaped in a little bit of different ways. Low melting point, does not conduct electricity. Metal, I'm just going to use copper and think about that. Well, this is hard because we could look at anything from mercury, which is a liquid, to sodium, which is going to be very soft, to tin, not tin. What would be one that's very hard? Iron. Iron would be a very hard metal. Low to high melting point, same thing. Conducts electricity. That's true for everything shiny, malleable, and ductile. So those are all the different properties. So again, memorize an example and then think about what the types of properties are of that example. That'll help you. Phase changes. This is our last learning objective for this one, I believe. So we have just these. And this will be a very important one, but also one that you're fairly familiar with. For example, we could come up with all the different names for the phase changes. So the ones that maybe you don't remember or don't know, if we go solid to liquid, this is called sublimation. And if we go a solid, solid to a gas. And then if we go from a gas to a liquid, this is going to be called deposition. And let's see, why is carbon dioxide called dry ice? Because it sublimes at room temperature. And here are the only calculations in this. Now, I actually haven't done these yet, so I'm going to wing it, see if I can do these. So we're looking at the amount of heat required to change 74.6 grams of water into steam. And so I'm going to draw this guy here as a reminder of what we're looking at, where we have our temperature and here we have our time. So if we're down here at negative 20 degrees Celsius, and then this is 120 degrees Celsius, this is going to be 0, this is going to be 100. If we start down here at negative 20 degrees Celsius, as we heat that water, it's going to go up to 0. Then it's going to change phases. And then we're going to go up to 100, and then we're going to change phases. And then we can go up to 120. Now these are all the different possible problems that we could do, I guess, all the different places that we could do calculations. And it's important to note that this here and this here are independent of the temperature change. So anytime we see a temperature change, we're going to be using this formula. That's here, there, there. And then at these two, we're just going to be doing some conversions. So in order to do these problems, you need to have information about specific heats and conversions. Now, those are listed probably in your notes by now, as well as in the book. And so you'll need to go to that information because it's not listed in the problem. So you have to have that to be able to do the problem. So if we have water to steam at 100 degrees Celsius, the only part of this entire sequence of events that we're doing is this one right here. We're not changing the temperature. All we're going is from 100 degree water, which is right here, 100 degree steam, which is right here. So we can do a conversion. 74.6 grams of water. 1 mole of water is 18 grams of water. And then 1 mole of water requires 40.67 kilojoules of energy. At least that is what my memory says. I'm hoping that's correct because, like I said, I haven't done these yet. Let's go through 74.6 divided by 18 times 40.67 gets us 168.5 kilojoules of energy. All right, so now we can go on to something very similar. This one does give us some information. I am not going to erase all of this, so let me see if I can get rid of this. It's taking a long time. Would have been easier just to leave erase the whole thing and redraw it. Oh well. Good enough. I wanted to leave that there because we now have a problem that's going to start here at negative 10 degrees Celsius here. So we're starting right where that arrow is actually, negative 10. And we're going to 126, which is actually just above here. So in this case, we have to do all 5 problems. We have to heat the ice up. We have to heat it when it's water. We have to heat it when it's steam. We have to go through 2 different conversion steps. So let's see here if I can do some color coding. Blue, we can do the different temperature changes. So this is going to be our ice. This is going to be our water. And over here is going to be our steam. So ice Q M S delta T. I'll put them over here so that I can attribute that to every single thing in here. So I starts at negative 10. Hold on. The mass, 866. Specific heat, 2.03. Change in temperature, 10. It goes from negative 10 degrees to 0 degrees as ice. Water, don't know the energy, that's what we're looking for. The mass is still the same, 866. Specific heat of water is 4.184. And the change in temperature is 100, because it goes from 0 all the way to 100. Steam now. Oops. $866 as well. 1.99 for the specific heat, and it goes through temperature change of 26. So add all those together, all the Q's, the Q here, And I'm going to change these into joules. So this is going to be 17.58 kilojoules. Remember that the answer that you get is going to be in joules. I'm just converting them right now. 866 times 4.184 times 100 is going to be a very large number. 362 kilojoules. I think I'm going to round this one to 17.6. 362 kilojoules. Steam, 866 times 1.99 times 26. 445. I think I did one of these wrong here. Hold on. 866 times 2.03 times 10 gets us 17.6. Oh, that looks right. All right, we're good. So we have those as our three different things there. So that is here, here, here. Now we can go to a different color and go here and here. We have 866 grams of water, 1 mole, 18 grams. We have, for the ice changing, is 6.01 kilojoules per mole. And we can do the other one. It's going to be the exact same thing, only here it's going to be 40.67. All right. $289 kilojoules. One 957 kilojoules. So I have all of these different numbers here, what we have looked at. Now all we have to do with them is to add them together. Once we have them all added together, we get our answer. Now, assuming that I have done everything correctly, which is never 100% guess, that is going to be our final answer for this entire process that occurred. All right. This is so pretty, I don't really want to erase it. Oh, there it goes. Now we're looking at rate of evaporation and some other properties here. So rate of evaporation is also known as the volatility of a liquid. What happens at the molecular level and how it's going to change with these things. Well, the ease at which the molecules are able to switch from a liquid to a gas is how we determine its rate of evaporation, its volatility. The greater the rate of evaporation, the lower the intermolecular force. So if we look at these, if we increase temperature, the rate of evaporation is going to increase because the molecules are moving faster. If the molecules are moving faster, the molecules aren't able to attract each other as well, so the intermolecular forces go down. Intermolecular forces go down, these molecules are able to break into the gaseous phase more easily. If you increase the surface area, you increase the rate of evaporation. This because there are more molecules exposed to that boundary between the liquid and the gas. So that is a big thing there. If we increase intermolecular forces, the rate of evaporation is going to decrease. So I have written here the opposite. If you decrease the intermolecular forces, that increases the rate of evaporation. That's because when we have less attractive forces between the molecules. They're able to break free into the gaseous phase more easily. Number 84, steam at 100 degrees Celsius causes more serious burns because condensation is an exothermic process. So as the 100-degree steam is changing into 100-degree water, it releases energy onto your skin, as well as it just being 100 degrees Celsius, so it sucks more, it hurts more. Phase diagrams. I don't have an example of one here. Let me see if I can draw one. So it's going to look something like this. This is going to be our solid. This is going to be our liquid. This is going to be our gas. Over here we have is it temperature? Actually, I think this is going to be pressure on this side. And temperature. Yeah, so that looks correct. So if we start here at a very, I'm not going to make up a substance because I'll get values wrong, but as we increase temperature, the substance can go from a solid to a liquid to a gas. But if we decrease the pressure enough, that same substance can go from a solid to a gas directly, like dry ice does. And so we end up skipping that liquid phase completely. So that's where the sublimation occurs. So solid, liquid, gas at certain pressures. So we can change at what point something will go through different phases by changing the pressure, and then we can increase and decrease the temperature. So I don't have a practice problem on here related to this, but most students find it pretty easy. So if after we go through the phase diagram practice problems in class, you still have questions about phase diagrams, I'll be happy to answer them. All right, the last stuff here. So, do I want to keep that? Nope, I think I'll get rid of this. Water is unique in that it has all three phases in normal atmospheric conditions. So, on the surface of our planet, it can go from a solid liquid to a gas under atmospheric conditions. Now, gas it evaporates. We can change it into a gas at a certain temperature once it boils, but it's also just really unique because of that hydrogen bonding that it does. All right, well, I'm tired, so I'm going to call it a good one there. Again, these phase diagrams, there's only a couple of problems on here and not a lot of good information, so if you're still struggling with phase diagrams, please come in and see me. Otherwise, we should be good.